I'm Ryu Kajie from Okayama University of Science, Japan. I will give you a presentation entitled Development of Machine Learning Based Object Grasping System Considering Shape Similarly. This is outline of my presentation. First of all, I will introduce the background and purpose of our study. Secondly, I will show you system configuration. Thirdly, I will show you image recognition using YOLO. Fourthly, I will show you experiments using a robot. And finally, I will give our summary. First, background and purpose of our study. In Japan, the population is shrinking and is expected to drop to 90 million by 2070. The working age population will fall to around 52%, creating labor shortages. To address this, there are growing focus on automation and efficiency. Robots using machine learning are being developed to help solve that problem. The Ministry of Agriculture is promoting smart farming, which combines traditional agriculture with advanced technology. Smart robots are being used to harvest tomatoes, broccoli, and sweet potatoes, among others. However, one major challenge remains: detecting complex and similar looks. This study focuses on a robot that uses machine learning to detect and grasp similarly shaped crops. We built a system using YOLO for object detection and a 3-axis robot for grasping. We will explain the system and our experiments. Next, system configuration. The system had two parts: a PC for inference and training, and a 3-axis robot. The PC runs Ubuntu and uses OpenCV for image processing, Ultralytics YOLO for detection and learning, and ROS2 for communication. All are implemented in Python. The robot is based on an industry 3D printer with a ESP32 and a pneumatic gripper. Here closer look at the robot. It has a webcam at the top for image capture. The pneumatic gripper is attached to the printer's head. Below it is a pneumatic valve that controls the gripper. The microcomputer is mounted at the bottom. There are two reasons why we choose a pneumatic gripper. The first is that it has bug durability, which makes it less likely to damage the target corpse. The second is that the gripper can be easily maintained by supporting air. For these reasons, we adapt a pneumatic gripper. We also calculate the gripping force. At 0.2 megapascal, the force at the gripper tips was 28.43 newtons. For communication, we use ROS2. The PC acts as a publisher and the ESP32 as a subscriber. Since regular ROS2 can talk to microcomputer, we use micro-ROS agent. Next, image recognition using real images are captured for the top webcam. We use air markers at the four corners to crop the bed area to 500 by 500 pixels. Then we calculate the object position for image coordinates. We choose a URL model that supports oriented bounding boxes, or OBB. This allows us to get more accurate angle and bounding boxes. We select YOLO 11 from amongst several OBB capable models. In YOLO, the model sizes are ordered as N, S, M, L, and X. This MAP50 score and detection speed vary depending on the model size. In this study, we prioritized an higher MAP50 score, so we used the X model for training. On the left is YOLO 11 and at the right is YOLO V8. The MAP50 score is higher for YOLO 11, showing a better detection performance. We used to crop dataset from the flow universe for training. This provided level image of various vegetables. Next, about experiments. In the experiment, the system tests a crops, calculate XY coordinates, send them to the microcomputer, and the robot moves to grasp it. We tested two types of grippers. Each was tested 100 times at 0.2 megapascal pressure. This was to confirm that the system works correctly. This is a video of the system in operation. The left side shows the crowless type, and the right side shows the crow type. Both grippers successfully pick up potatoes. The crow type gripper had a 83% success rate, and the crowless one had 56%. These results confirm the effectiveness and reliability of the system. Here is the table showing the detailed experiment results. The number of times YOLO successfully detected a potato is shown as recognition, and the number of times the potato was successfully grasped after detection is shown as grasp. In the crowless type, there are no crow, so the potato often strip out, resulting in 44 grasping details. For your detection, variation occurs due to factors such as air marker recognition in pre-processing and difference between individual potatoes. Finally, summary in this presentation. We trained your object detection model and successfully detected objects. We communicated with the robot we lost and moved it successfully. Our experiments confirmed it. The system works as intended. Thank you for listening.